Hello, here we are in week 6. This is the last week of new material before the midterm. The midterm is going to be in week 7, and you're going to want to go to the curriculum file to see when your midterm is going to be, because as you can see, it's lecture dependent. And if you're not sure which lecture you're in, then you want to go onto your schedule in Solar to find out. Or it should say in Blackboard. Earlier in the week, and maybe a little bit at the end of this week, you'll be reviewing in recitation, and there will be review material that will be available to you on Tuesday night. Let me go back to resources. You're going to click on exam information. And then two things are going to show up at 7 o'clock on Tuesday night. You'll have midterm review material. You'll click on here. And you'll also have, go back to here, you'll have information about Gradescope. You'll get an email. You'll have how to sign up, just logistics for the test. And then you'll also have a sample exam. A sample exam will be available until 6 p.m. on Sunday night. And let me just go over to here just so you can get a visual once you're logged into Gradescope. And again, you're going to be looking for that invite into Gradescope on Tuesday on your Stony Brook email account. And once you're in, you'll see the sample exam. Then you'll follow the instructions that are posted on Blackboard. And this is worth it's worth up to 6 points on your midterm grade. And really the whole purpose, this is going to be by design a pretty easy thing. It's 3 quick questions to give you the opportunity to work with Gradescope, get used to uploading. It's a little bit different from Blackboard. Maybe even it's a little more forgiving than Blackboard. 2 things that I want to say about this, which you'll be able to read this, but I'll give you the heads up on it, is these problems, there are a substantial amount of problems for you to work with. They're additional problems. They're not intended to substitute for the material that's given to you in the videos, on the PowerPoint slides. So make sure you do all that other stuff also. The other thing is that for these problems, the solutions are not going to be posted. In a different semester, in air quotes, normal semester, I would post the solutions. But because you have an open book test, I'm reticent to just post the solutions because I don't want you just to say, oh, gee, I never got a chance to look at the review sheet. Maybe I'll just go and I'll download the solutions like 5 minutes before the test. I want you to work through the problems. So where do you get the answers? You're going to be talking about them in recitation, and don't go into recitation cold and expect your recitation instructor to just kind of spoon feed it all to you. Go through the material before recitation and come in prepared with questions. Try to identify where your weak spots are. And you're probably not going to get through all the questions by yourself. Don't expect to, but at least know what you're unsure of. You can also ask at office hours, whether they're my office hours, your recitation instructors' hours. You can also ask questions about getting the solutions at the Math Learning Center. And continuing on with the administration, what had happened is I took the derivative for trigonometric functions and I moved it from week 5 to week 6. I was just trying to balance out the workload between these 2 weeks. And the problem was I had made this homework in advance. Shame on me for doing something in advance. I messed up the availability date because you probably saw week 5 show up on Lumen and then it went away and now it's here again. But there were a few questions, I believe it was 4 of them that were about trig derivatives. So when you go to Lumen, what you're going to see at the end, just so you're not alarmed, is these last few questions. It says that they were withdrawn. You'll see them again next week. don't just ignore them. You don't have to bother with them. The good news is that when you open the assignment, you'll already have 4 points. You're welcome. Getting on to the lecture material. This week, as you saw on the curriculum, this week I'll be covering derivatives for trigonometric functions. I'll be covering quotient rule and chain rule. And again, all of this is going to be on the midterm. In order to understand why the trig derivatives are what they are, let's look at the graphs. Start off by sketching one period of the sine of x graph. It doesn't have to be anything fancy. Then once you have that, directly under it, sketch its derivative. Pause if you need to. Notice that I already have the horizontal tangent lines drawn in. Therefore, f prime will be 0 here and here. Slopes are positive. All the way down here, slopes are negative. Slopes are positive. That's going to make the graph look like this. Make sure you understand where this graph came from. And then zooming out, looking at the graph, well, notice that this is the graph of cosine. And therefore, I'll conclude that the derivative of sine of x is equal to cosine of x. Now, doing the same thing in order to find what the derivative of cosine of x is, go ahead and put another plane directly under and sketch the derivative of cosine of x and see what you get. And again, pause here if you need to. Now, because we're only looking at one period, we're not going to see all the horizontal tangent lines. I mean, the obvious one is here. I'll draw that in. But if we continued on drawing, this is another peak. Over here, here's another peak. So then here at 2 pi, the tangent line is going to be, the slope of the tangent line is going to be 0. And also here at rotation 0. So I'll put those in. And then from here to here, the slopes are negative. From here to here, the slopes are positive. That's going to make the derivative graph look like this. And again, looking at this graph to see what it's the graph of, well, it looks like sine, but it has a transformation. It has actually a reflection. This is the graph of y is equal to negative sine of x. It's reflecting about the x-axis. Therefore, I'll conclude that the derivative of cosine of x is equal to negative sine of x. Now, maybe you'll be adding these onto, if you're developing a reference sheet with all your derivative rules, definitely add these on. And going right into an example, you're asked to find the derivative of f of x equals x squared times sine of x. And hopefully you're recognizing that this is product rule. I'll put the product rule on the bottom here for reference. Developing the chart, f would be x squared, g would be sine of x. Their corresponding derivatives would be f prime is equal to 2x. And using this fact, g prime will be cosine of x. Therefore, f prime of x would be 2x times sine of x plus x squared times cosine of x. No simplification to be had here. This would just be the answer. Here's one to practice on your own. You'll find the derivative of y is equal to 4x times cosine of x. Pause now. Here's the solution. Creating the chart, f is equal to 4x, g is equal to cosine of x, therefore f prime would be 4, g prime would be negative sine of x. So dy dx is 4 times cosine of x plus 4x times negative sine of x, right, f g prime, and then simplifying the signs gives the final answer of 4 cosine x minus 4x sine of x. I'll go back and talk about the other 4 trig derivatives in a minute, but first I'm going to show you quotient rule. And I'll say that when 2 differentiable functions are divided, then you'd use the quotient rule in order to take the derivative. I'll give you the formula. If it's in the format of f over g prime, then very similar to the product rule, it looks exactly the same in the numerator except for the sign. It's f prime g minus f g prime all over g squared. And the important thing to know about this is that it's not g prime, it's just g. Right? And this is also applicable only where g is not equal to 0. And this is just housekeeping. You're not going to have to be conscious of that necessarily while you're taking the derivative. For example, if you're asked to find y prime, given that y is equal to, has a numerator of x squared plus x minus 2, and a denominator of x cubed plus 6, then f would just be the numerator, right? If I'm putting it in this format, x squared plus x minus 2. G would be x cubed plus 6, the denominator. And just like with product rule, I'll get the corresponding derivatives. F prime would be 2x plus 1. G prime would be just 3x squared. And then following the formula, then y prime would be f prime g minus f g prime all over g squared. Plugging in, it would be 2x plus 1 times x cubed plus 6 minus x squared plus x minus 2, this is f, times g prime, 3x squared, all over x cubed plus 6 squared. As far as the simplification here, you're going to simplify the numerator but not the denominator. So I'll start with combining these, right? I'll multiply the binomial times the binomial. The result of that will be 2x to the 4th plus 12x plus x cubed plus 6, and then minus, I'll distribute the 3x squared into the trinomial. That'll be 3x to the 4th plus 3x cubed minus 6x squared. And then, as I said, just leave this in its factored form. The denominator stays x cubed plus 6 squared. More simplification to be had in the numerator. Rewriting these terms, 2x to the 4th plus 12x plus x cubed plus 6, distributing the negative. So then the other terms become minus 3x to the 4th minus 3x cubed plus 6x squared. Then combining like terms, numerator becomes negative x to the 4th minus 2x cubed plus 6x squared plus 12x plus 6, and that's all over x cubed plus 6 squared. The nice thing about quotient rule is that because it's division, because it's a fraction, it's a lot easier to recognize when you have to use quotient rule compared to product rule when it's not always so obvious that it's multiplication. Next example, bringing this up one level, in this question you're asked to find the equation of the tangent line to the curve y is equal to e to the x over 1 plus x squared. And we're finding the equation of the tangent line at the ordered pair of 1 comma e over 2. Now remembering to get the slope, you'll get the derivative. And I'll use dy dx here. And let me just introduce this. This is going to be helpful to start to think like this as we go down the road and take derivatives of more complex things post-midterm. Think of this instead of dy dx. Think that we're taking the derivative with respect to x because that's the variable of y. And then creating the chart. Numerator, or f, is e to the x. Denominator, or g, is 1 plus x squared. F prime is e to the x. G prime is 2x. And therefore, the slope, or dy dx, would be f prime e to the x, g, 1 plus x squared, minus f times g prime e to the x times 2x, all over g squared, 1 plus x squared squared. And then simplifying the numerator. Right? In this case, because of the format of this, I'm going to factor out the e to the x. And then what I have left is 1 plus x squared minus 2x all over 1 plus x squared squared. And that's as simplified as this is going to get. Therefore, I'll say that this is the general slope. And in order to find the equation of the tangent line, I need to find what the slope is at 1 comma e over 2. So I'll find that. In other words, I'm going to plug 1 in for x. And that's going to look like this, e to the 1, inside of the parentheses, 1 plus 1 squared minus 2 times 1 over 1 plus 1 squared, and that's all squared in the denominator. And then simplifying this, e to the first is e. Inside of the parentheses in the numerator, it's 1 plus 1 minus 2, all over 1 plus 1 squared. And then that's going to simplify, well, just look what's happening inside of the parentheses in the numerator, 2 minus 2, that's actually going to zero out the whole thing. Well, so 0 over 4, which is 0. Right. So if the slope is 0, then when we plug into the point slope formula, y minus y1 equals m times x minus x1, right. Here's your x1, y1, here's your slope. It would be y minus e over 2 equals, just to be formal, I'll plug it all in the first line. So 0 times x minus 1. And again, this whole thing is going to just zero out. I'll add e over 2 to both sides to solve for y. And therefore, the equation of the tangent line to the curve y is equal to e to the x over 1 plus x squared at 1 comma e over 2 would just be y is equal to e over 2. Next, I'll talk about the derivative of tangent of x. And I'm just going to say the derivative of tangent can be derived from the trigonometric identity of tangent of theta equals sine of theta over cosine of theta. And you can find the derivative of this now that you know quotient rule. Right? Then tangent of theta would be the derivative of sine of theta over cosine theta, where f is equal to sine of theta, g is equal to cosine theta, and then putting their corresponding derivatives, f prime is cosine of theta, g prime is negative sine of theta. Then tangent of theta prime would be f prime g, cosine of theta times cosine of theta, minus fg prime, which is sine of theta times negative sine of theta, all over g squared, which is cosine of theta squared. And now simplifying the numerator, this is cosine squared. So I'll put that here. And then negative times a negative is a positive. Sine times sine, sine squared theta. Hopefully this is causing you to think of another trigonometric identity. And then this is all over cosine squared of theta. Right. Numerator becomes 1. Right. This is the Pythagorean identity. And then simplifying this, this would be secant squared of theta. So another thing to put on your reference sheet is that, and we just kind of, to be consistent with your other ones, I'm going to make this in terms of x. The derivative of tangent of x is secant squared x. And I'm going to take a second to talk about the 6 trig derivatives. Certainly your exam is going to be open book. Therefore, I recommend that on the reference sheet you put all 6 trig derivatives. But in a regular non-online world, you have to kind of make a choice, decide like what kind of a learner you are. Because going forward, if you take Calc 2 and it's not in an online open book format, you have to decide, because what some people will do is they don't want to clutter their mind up with remembering all 6. And therefore, what they'll do is they'll just memorize the derivatives for sine of x and cosine of x. And then if they needed the derivative of tangent, they would just quickly go through these calculations to get the derivative of tangent using quotient rule. And that's going to be the same thing for the other 3 trig functions. Now, maybe you're a memorizer and you'd rather not have to bother to do this on a test and you just want to memorize the other 4. Certainly that's fine. And again, it's just giving you some food for thought for and just make the personal decision. No right or wrong answer. Jumping right into an example. Using the derivative of tangent, you're asked to find y prime when y prime is equal to e to the theta. Notice I like to give you different variables to not get you so stuck in only being able to take the derivative when it's in terms of x. So the function here is, or not even necessarily a function, the curve here is y is equal to e to the theta times tangent of theta minus theta. Right? So this is going to require product rule. F is equal to e to the theta, g is equal to tangent of theta minus theta. And taking the derivatives, f prime is e to the theta, g prime, using this fact, would be secant squared theta, and then this is the variable. Think of this as x, right? The derivative of x is 1, and therefore the derivative of theta is 1. And remember, if the theta really rocks your world and you can't like see the derivatives as easily, then just rewrite this in terms of x and work the whole problem through an x. But make sure, in order to get full credit for the answer, convert it back to theta when you're done. Y prime would be f prime g e to the theta times tangent of theta minus theta, plus, because we're using product rule, f g prime e to the theta times secant squared theta minus 1. And fine to just leave this like this. We're not... in the previous example, I factored out the e to the theta because I was going to plug in a value into this and it made it easier to evaluate. But here, this is the final answer. Don't bother to factor out the e to the theta. To give you some practice using quotient rule, I'll put these 3 trig derivatives up, the 3 that you know so far. By the end of the slide, you'll know all 6. And take the time now to convert secant of theta into a fraction and then use quotient rule to find its derivative. And then in your final answer, use trig identities to convert it so that you don't have any fractions in your answer. Pause now. If you're stuck at the beginning, remember that secant, again using trig identities, you convert that into a fraction by turning it into 1 over cosine of theta. And then constructing the chart, numerator f is 1, g is equal to the denominator cosine of theta, and then derivatives, f prime is 0, g prime is negative sine of theta. Then the derivative of 1 over cosine of theta would be f prime g, 0 times cosine of theta, minus f g prime, and I won't bother to put the 1, negative sine of theta here, all over cosine squared theta. And then this whole term is going to zero out. Negative times a negative would make the numerator positive sine of theta, and then over cosine squared of theta. And then to get rid of the fraction, what I'm going to do here is write this out as two separate fractions. I'll write 1 over cosine of theta, and then what do I have left over? Sine of theta and cosine of theta. So this is 1 over cosine of theta times sine of theta over cosine of theta. And again, using trig identities, 1 over cosine theta will become secant theta. Sine of theta over cosine of theta will become tangent of theta. So new box. The derivative with respect to x of secant of x is going to be secant of x times tangent of x. And now at this point, I'm not going to derive the other two. I'll just give them to you. The derivative of cosecant of x is negative cosecant of x times cotangent of x. And the derivative of cotangent of x is going to be negative cosecant squared of x. And you can see the patterns here. If this is positive secant of x, then cotangent is negative cosecant squared of x. And here this is secant of x, tangent of x. This is cosecant, cotangent, but then again negated. So there is a little pattern there if you're a memorizer. Watch how fun this next example is. You're asked, where does the function secant of x over 1 plus tangent of x have horizontal tangents, singular or plural? Start to think about what it means to have a horizontal tangent. And I'll talk about that in a moment. But start off by seeing that it's asking about the tangent, therefore you're going to find the derivative. This is a fraction, therefore you're going to use quotient rule to find that derivative. So I'll start the chart over here. F is equal to secant of x, g is equal to 1 plus tangent of x, and get the corresponding derivatives. F prime is equal to secant of x times tangent of x. G prime, this is going to zero out. Therefore, g prime is secant squared of x. So using quotient rule now, putting this all together, you have f prime times g, secant of x tangent of x, times, and make sure you put this in parentheses, 1 plus tangent of x, minus f g prime, secant of x times secant squared of x, and that's all over 1 plus tangent of x squared. Now, in order to simplify this, I'm going to factor out the common factor of secant of x. It'll look like this, secant of x, and then what's left here, as I'm rewriting this, I'm going to distribute the tangent of x into the binomial. That'll make this tangent of x plus tangent squared of x. And then when I factor out this secant of x, I'm left here with minus secant squared of x. And rewriting the denominator, 1 plus tangent x squared. Now, using a trig identity, maybe a less commonly known one, tangent squared theta minus secant squared theta is equal to -1. Therefore, I'll rewrite this, secant of x times tangent of x minus 1, all over 1 plus tangent x squared. And now this is where the horizontal tangent comes through. If you have a horizontal tangent, well, that means that the slope, let me just draw a little picture here. a horizontal tangent means that on f, this x value is a place where the slope of the tangent line is equal to 0. That's what makes it horizontal. And therefore, f prime of x, because we know that the derivative is synonymous with the slope of the tangent line, so it's a place where the derivative is equal to 0. And then I'm going to solve this for x. And the first thing to know is that for secant of x, there's never a place on the secant graph where secant of x is 0. Remember, it's like a whole bunch of like parabolas with asymptotes. Right? So we don't have to consider that factor. Now, jumping to the denominator, 1 plus tangent x squared also is never 0, and let me show you why. Looking at a period of tangents, that'll look like this. And here's the, just write this, y is equal to tangent of x. And at this point for each of the periods, that's where the graph is at 0. And then if I shift the graph up 1, this would be the graph of y is equal to 1 plus tangent of x. And then if I square this, then that means that everything here, all these negative values of y are going to become positive, and the graph would look like this. So here we are at 1, and this is 1 plus tangent of x squared. Notice that you'll have infinitely many parabolas for all the periods. Notice how there's no x value that'll make this graph 0. So with these two factors not affecting where this is 0, the only one we have to consider is tangent of x minus 1. So let me just say that. F prime of x would be 0 wherever tangent of x minus 1 is equal to 0. And I'll solve this for x algebraically, adding 1 to both sides, and then looking at this and seeing where this would be an equality. Well, when the angle of rotation is pi over 4, that would be the case. Therefore, x is equal to pi over 4 would be one of the solutions, but of course there are infinitely many periods, so therefore this is going to repeat itself every pi, because pi is the period of tangent. This only happens once in a period, and I'll define n as an integer. So where does f of x equals secant of x over 1 plus tangent of x have horizontal tangents? Well, that's when x is equal to some multiple of pi over 4. Next example, looking at the object at the end of a spring. Remember, a spring has a natural stretch, so if it's stretched past its resting or natural position 4 centimeters, then released, and we'll consider the release time to be time is equal to 0. I'll give you a picture to show this. Here's the spring at rest. The object is, so the spring at rest would be here, and it's pulled now 4 centimeters past that natural resting position. Right? Then when it's released, the object's position at time t can be determined using the following function. S for position, S of t is equal to 4 times cosine of t. And if you're asked to find the velocity and acceleration based on time t, then remember that you'd have to get the derivative of s of t in order to get velocity. Taking the derivative of this is a nice easy derivative. It would just be negative 4 times sine of t. And then to get the acceleration, you'd take the derivative of velocity, which then essentially gives us the second derivative of position. and taking the derivative of negative 4 times sine of t. Derivative of sine is cosine. The negative 4 stays in front. Therefore, acceleration would be negative 4 cosine of t. The next slide in the PowerPoint pack is basically just everything that you've learned so far about derivatives. You have power rule, derivative of e to the x, product rule, quotient rule, and the 6 trig derivatives. Nice to have it just all in one spot for reference purposes. In this next slide, I'll show you a special case to illustrate that sometimes it's easier to simplify a function than it is to use the quotient rule when you have a fraction. You're asked to differentiate. Numerator is 3x squared plus 2 rad x. Denominator is x. First time I'm around, I'm going to show you how to do it with quotient rule. F would be the numerator, 3x squared plus 2 rad x. G would be the denominator of x. And I'm going to write this in a more derivative-friendly format. I'll write it as 3x squared plus 2x to the 1/2. Then f prime would be 6x plus 2 times 1/2, x to the negative 1/2. And then simplifying, this would be 6x plus 1 over rad x. I'll turn this back into a radical. G prime would just be 1. Therefore, f prime of x, let me just box these first. So here's f prime, here's g and g prime. And really this time, f prime of x would be f prime times g, 6x plus 1 over rad x times x, minus f times g prime, 3x squared plus 2 rad x times 1, all over x squared. And then to simplify the numerator, I'll distribute the x into the parentheses here. Becomes 6x squared plus, and I'm going to take this off to the side first to simplify this. I'm going to write x over rad x as x to the first over x to the 1/2, recognizing that these are the same bases. Therefore, I can use exponent laws. 1 minus a half makes this whole fraction simplify to be x to the 1/2. And when I write it over here, I'll write it as a radical. And then all I have to do for the last two terms is just distribute the minus. Becomes minus 3x squared minus 2 rad x. Write x squared again in the denominator. And if you scan the numerator, you have like terms. You have x squared terms and you have radical x terms. These simplify to be 3x squared, and then plus radical x minus 2 radical x simplifies to be minus radical x. And this is all over x squared. Now, I'm going to show you the trick that I'm going to end up using at the beginning here in the other method. I'm using the fact that if I have a plus b over c, I can write this as two separate fractions, making this the common denominator. It would be a over c plus b over c. Normally we have this and we want to write it as one fraction, but it's helpful in the other direction sometimes as well. So I'll write this as 3x squared over the denominator of x squared, and then it will be minus rad x over x squared. And now using common bases and exponent laws, I'm going to cancel these x squareds. That makes the first term 3. And then for the second one, go ahead and use the same technique as we did here to write this as x to a power. X to the 1/2 minus 2 would be x to the negative 3 over 2. And let's just leave this like this for now. In the second method, as I said, I could have done this before I took the derivative. So I'll write this as 3x squared over x plus 2x to the 1/2 over x. And then simplifying, this becomes 3x, and this 1/2 minus 1, this becomes 2 times x to the negative 1/2. And I'm not going to write this as a radical because I still have to take the derivative. I want this to be in power function format. And therefore, f prime, first term would be 3. Second term, the negative's going to come in front. So it'd be 2 times negative 1/2 times x to the negative 3/2. And then simplifying this becomes 3 minus x to the negative 3/2, which is the same answer that we got here when we used quotient rule. So same answer, but look how few steps this took versus look how many steps this took. And again, maybe you're comfortable with quotient rule. I'd rather, if you can recognize this and use it, I'd rather you do that, because here there's so many places that you could just make a little mistake. Then either way that you did this on an exam, I would accept it, either technique, as long as you document it properly. All right. Then just to simplify, final answer, I would take that x to the negative 3/2, and I write it as a radical in the denominator. Final answer, 3 minus 1 over the square root of x cubed. Now we have the ability to look at functions that are going to require both the product rule and the quotient rule in order to take a derivative. For example, you're asked to differentiate. Numerator is 1 minus x times e to the x. Denominator is x plus e to the x. Right. Now I'm going to start off with quotient rule, which work from the outside in, macro to micro. That makes f 1 minus x times e to the x. G will be the denominator, x plus e to the x. And now, so far that's quotient rule. And then when I go to find f prime, I see here that I need to use product rule to take the derivative of the numerator. Right? So I'll make x e to the x, I'll give it its own chart. And instead of using f and g, I'll use u and v for the two factors. So this will become uv prime is equal to u prime v plus u v prime. Therefore, f prime will be 0 for the 1, and then minus the product rule, u prime v, 1 times e to the x, plus uv prime would be x e to the x. And I'll simplify that to negative e to the x minus x e to the x. G prime is a pretty straightforward derivative. It'll be 1 plus e to the x. Now, coming over here to finish up the quotient rule, it'll be f prime g minus f g prime all over g squared. So negative e to the x minus x e to the x times g, x plus e to the x, minus f, 1 minus x e to the x, times g prime, 1 plus e to the x. All four of these are binomials, therefore I'll put each of them in parentheses. And this will all be over x plus e to the x squared. As has been the case in other examples, I'm going to leave the denominator as is, and I'm going to simplify the numerator. This times this becomes negative x times e to the x. Right. Now, this times this, do this one time on the side, it'll be e to the x times e to the x, which is e to the x squared, and then the powers can be multiplied, and therefore this will be e to the 2x. So here I'm going to put minus e to the 2x. Then this times this is going to be negative x squared e to the x. This times this will be negative x, and I'll just go right to e to the 2x, multiplying e to the x times e to the x again. Now for this binomial times a binomial, it'll be 1 plus e to the x minus x e to the x minus x e to the 2x all over x plus e to the x squared. Okay. Now I'm rewriting all these terms. All I'm doing to get from this numerator to this one is distributing the negative inside of the parentheses. So this will be negative x e to the x minus e to the 2x minus x squared e to the x minus x e to the 2x minus 1 minus e to the x plus x e to the x plus x e to the 2x over x plus e to the x squared. There are a number of like terms here. The x e to the x's will cancel. The x e to the 2x's will cancel. And I believe that's it. All right, so I'm rewriting the terms that are left. Negative e to the 2x minus x squared e to the x minus 1 minus e to the x, and this will be over x plus e to the x squared. That's the final derivative. I'm finished talking about quotient rule for now. Moving on, first I'm going to review a concept from pre-calculus, composition of function. For example, if you're given two functions, let's say f of x is the square root of x and g of x is x squared plus 1. If you're asked to find f of g of x, well, you should know that you would plug g of x into the f of x function. In other words, we're trying to find f of x squared plus 1, and then this gets plugged into here. The composed function f of x of g of x would be square root of x squared plus 1. Then, just to recall the vocabulary, we would say in this situation that x squared plus 1 is called the inner function, and then the outer function is here. That would be square root of x. Next, looking at a composed function, h of x is equal to x cubed minus 1, all raised to the 100th power. If you're told that this is in the format of f of g of x, you should be able to look at this and determine which is the separate f of x and which is the separate g of x, just like we had here before the composition. And you should be able to see that the inner function g is x cubed minus 1, and the function that it was plugged into to get h of x was x to the 100. And if you're not sure about that, go off to the side and do f of g of x to show that to yourself. You should be able to, at this level, readily recognize that this is a composed function, and you should be able to dissect which is the inner function and which is the outer function. And the reason for that is now we're going to be taking derivatives of composed functions. And in order to do so correctly, you need to be able to decompose the function. And when I say decompose, I mean pull it apart to be able to identify separately the inner function and the outer function. So when you take the derivative of a composed function, you have to take the derivative both of the inner function and the outer function. And going back to that format, where h is in the format f of g of x, then h prime of x would be f prime of g of x. And notice that this is g and not g prime. So it's f prime of g of x times g prime of x. The way you would say this, it's the derivative of the outer function times the derivative of the inner function. Chain rule is the procedure for taking the derivative of a composed function. For example, using that function from the previous slide, h of x is equal to radical x squared plus 1. Remember how we said that the inner function was x squared plus 1, and the outer function was square root of x. Then taking the derivative just of f, that would be 1 over 2 rad x, because that's the derivative of square root of x. And then f prime of g, well, I just take g and plug it into here, this radical x in the denominator. F prime of g would become 1 over 2 radical x squared plus 1. Then g prime is just 2x, and pulling this all together, then h prime of x would be f prime g times g prime. Then here's f prime g, so that'll be 1 over 2 radical x squared plus 1 times g prime, which is 2x. And then I'll simplify this and write it as one fraction. I'll cancel the 2's. Now the x will go in the numerator, and the denominator will be radical x squared plus 1. Doing it this way is actually the long way around. There are a lot of steps. We can streamline this using a u substitution, and I'll show you this using the second composed example. H of x equals x cubed minus 1 to the 100th power. And what I'm going to do is define the inner function as u in order to simplify this and make it easier to take the derivative. I'll say u is equal to x cubed minus 1. And then I'll rewrite this as it's not going to be h to the x because the variable now is temporarily u. It'll be h is equal to u to the 100. And then h prime will be u to the 100th prime times u prime. Remember, derivative of the outer function, because essentially that's what this is. It's like when we put the u in here, we create the outer function. So it's derivative of the outer function, but then we have to multiply it times the derivative of the inner function, which is u. So u to the 100th prime times u prime. So I'll take the derivative of the outer function. This, using power rule, will be 100 times u to the 99th, and I'll just bring down the u prime. And now u prime, this is also an easy derivative. This will just be 3x squared. And then I'll rewrite this because since this originally had a variable of x, your final answer also has to have a variable of x. It's like this whole u thing is happening backstage. So now plugging back in, now that both derivatives have been taken, this becomes 100 times x cubed minus 1 to the 99th, and then times u prime becomes times 3x squared. And not a bad idea to do a little housekeeping at the end, combining like factors. So 100 times 3, we'll have 300, and it just looks a little nicer to put the x squared in front, and then I'll put the x cubed minus 1 to the 99th. As you can see, a lot less steps to use the u substitution, and again, can't stress it enough, makes it less likely for you to make a silly mistake along the way. All right, so now knowing this, let's go back to radical x squared plus 1. I'll define u as the inner function, x squared plus 1. And nothing to say that I can't take the derivative of u here while it's fresh in my mind. Either way is fine. And then this becomes radical u. Therefore, h prime will be the derivative of radical u, the derivative of the outer function, times u prime, derivative of the inner function. And the derivative of this is 1 over 2 rad u. And I'll rewrite the u prime. And now all the derivatives have been taken. I'll substitute back in for x. this factor becomes 1 over 2 radical x squared plus 1 times 2x, and writing this as a single fraction. Again, as we saw in the previous slide, the 2's will cancel, the x will go in the numerator. Derivative is x over radical x squared plus 1. Next example, finding the derivative of y is equal to sine of x squared. X squared is in parentheses. And I'll make x squared the inner function. I'll call it u. And since we're using Leibniz notation, just to give you some experience seeing this, instead of using u prime, I'll be consistent and I'll use du dx because we're taking the derivative of u where x is the variable. And then this is just power rule. This becomes 2x. And then rewriting this with u, it becomes sine of u. This is still y. Now watch the notation here. When I take the derivative of y, because this is u, for now I'm going to write this as the derivative of y with respect to u. Derivative of sine is cosine, so cosine of u. And then I'll put du dx here to keep that u here. Now I'm going to rewrite this in terms of x. Therefore, I'll convert this to be dy dx, the derivative of y with respect to x. Now this will become cosine of x squared. Du dx, I'll substitute in 2x. And then now I'll reorder this because it's a little cleaner to write 2x and then the cosine of x squared. Now there are two ways that we can take the derivative in the next example. You're asked to find y prime of y is equal to sine squared x, and make sure you see that this is different from this and how it's different. Now I'm going to write this for the first way I'm going to take the derivative as sine of x squared, and therefore I'll make sine of x the inner function, which I'll label as u, and then I'll rewrite this as u squared. Take the derivative of u prime will be cosine of x. Then y prime will be, I'm taking the derivative of the inner function, so u squared will become 2u. So y prime will be 2u u prime, derivative of the outer function times the derivative of the inner function. Now I'm ready to plug back in. This will become 2 times sine of x for u, and then u prime cosine x, 2 sine x cosine x. Right? So I did this using chain rule. The second way to do this, because you don't always have to use chain rule in this case, would be to use product rule. Instead of writing this as sine x squared, I wrote this as sine x times sine x. Then here we have f, here we have g, and this will become f prime g plus f times g prime, right? Cosine x sine x plus sine x cosine x. And then combining these, this is really also sine x cosine x with just the factors flipped. And therefore, they're like terms, and I can write this as 2 sine x cosine x. Here's a problem for you to try on your own. Find y prime, given that y is equal to e to the sine x. Pause now. In this case, the inner function is the exponent. So I'll label u as sine of x. And I'll take the derivative, u prime is cosine of x, derivative of the inner function. Then y prime is equal to e to the u prime, which is e to the u, times u prime, derivative of the outer function, times the derivative of the inner function. And then plugging in, y prime would be e to the sine x times cosine of x. And give you some practice with higher order derivatives. Go ahead and find the first three derivatives of y is equal to. Right now, find the first three derivatives, in other words, f prime, double prime, and triple prime, of y is equal to x cubed plus 2x minus 16. pause now. This is just power rule. Therefore, y prime would be 3x squared plus 4x minus 16. Then y double prime would be 6x plus 4. And y triple prime would just be 6. And the reason I'm having you go through this is that I want you to see about what's happening with the fourth derivative and even the fifth. If I take the derivative of 6, then that would be 0. And then I want you to see that from there forward, any other derivative would be 0 also. Now that isn't going to be the case with something like cosine. If I took the second derivative of cosine, well, if I took the second derivative of u, I would take the derivative of cosine, which would be negative sine x. U triple prime would be negative cosine x. Fourth derivative, this would be negative sine of x, and that would be sine of x. And you can maybe start to see the pattern here. Then going on and on, there would be infinitely many derivatives. Right? So now jump down to my conclusion here. Some functions, like trigonometric functions, are going to have infinitely many derivatives, whereas something like a polynomial will have a finite number of derivatives. Next example, find f prime of x, given that f of x is equal to 1 over the cube root of x squared plus x plus 1. Now, first thing I'm going to do is I'm going to write this in power function format, almost. This is to the 1/3 power, and then moving it into the numerator, it becomes x squared plus x plus 1 to the negative 1/3 power. And in this format, you can see, hopefully, that u is going to be what's inside of the parentheses, x squared plus x plus 1. And as long as I'm here, I'll find u prime, 2x plus 1. And then this will come down here as u to the negative 1/3, and that'll make f prime of x u to the negative 1/3 prime times u prime. Again, can't say it enough. Derivative of the outer function times the derivative of the inner function. This, I'll use power rule to find the derivative. It'll be negative 1/3 u to the negative 4/3 times u prime. And then plugging back in, it becomes negative 1/3 times x squared plus x plus 1 to the negative 4/3. U prime, I'll put in inside parentheses, 2x plus 1. Now, cleaning this up, I'll put the negative in front, 3 in the denominator. Then I'll put this in the denominator, x squared plus x plus 1. It becomes positive 4/3. I'm putting just the positive there for emphasis. And then the 2x plus 1 will go in the numerator. Remembering when I asked you to find y is equal to e to the sine x, well, the derivative of that, then let's look at something comparable, but the same but different. Let's differentiate y is equal to e to the x sine x. Start it off the same. I'll make the exponent x sine x u. Then when I go to take the derivative, I see that this is actually multiplication. It's x times sine x. Therefore, f is x, g is sine x, f prime is 1, g prime is cosine x. Therefore, u prime will be sine x plus x times cosine x. And then coming over here, y would become e to the u. Y prime would be e to the u prime times u prime, which would be e to the x sine x plugging back in for u. And then u prime, I'll put this in parentheses, sine x plus x cosine x. Now, watch what happens here. Before, you had a product rule in the exponent. See what happens here when y is equal to e times cosine of 2 theta. Well, I'm going to start it the same way. I'm going to make u cosine of 2 theta, and then this becomes e to the u. And notice I'm kind of going through the steps a little bit differently each time. I want you to understand that there are different ways to go through the problem and to notate it. They're all correct. Right? It just depends on which way your mind is thinking about it, right? Because sometimes I'll take u prime first. Other times I'll write this up first. It doesn't really matter. All right, so I'll write this as e to the u. And then y prime will be e to the u, because I've already taken the derivative of this, times u prime. And now when I go to find the derivative of u, I can see that this has its own inner function of 2 theta, and I've already used u, so when I go to find u prime, I'm going to, again, do a u substitution, only I'll use v instead as the variable for the inner function. So this becomes cosine of v, and then when I go to take the derivative of u, it's cosine of v prime, because this is the outer function, times v prime. And then cosine of v prime would be negative sine of v. V prime, this would just be 2. Again, think of this as 2x. And so I'll put the 2 here. And this is a coefficient. I can just put this in front. It'll be negative 2 sine of v. And I'll plug in for v. It becomes negative 2 sine of 2 theta. Now I'm ready to plug in for the u. This e to the u becomes e to the cosine 2 theta. U prime is negative 2 sine of 2 theta. Now my whole derivative is in terms of theta, hooray. And I'll just rewrite this. I'll put the negative 2 sine of 2 theta in front, and then times e to the cosine of 2 theta. You don't want to misinterpret this accidentally as subtraction, so it's cleaner to write it like this. Lastly, I'll give you a couple more fun examples. Find the derivative of y is equal to 2x plus 1 to the 5th times x to the 4th. Recognizing that on a macro level, you have product rule. It's this times this. And then breaking this up, f would be 2x plus 1 to the 5th. G is x to the 4th. And then using chain rule to get f prime, u, the inner function, will be 2x plus 1. Therefore, this is u to the 5th. Then f prime would be 5u to the 4th times u prime. U prime is 2. Then substituting back in, this becomes 5 times 2x plus 1 to the 4th times 2. And I'll combine the 5 and the 2. 10 times 2x plus 1 to the 4th is f prime. G prime would just be 4x cubed. Therefore, y prime would be 10 times 2x plus 1 to the 4th times g, x to the 4th, plus f, 2x plus 1 to the 5th, times g prime, 4x cubed. And I'll just rewrite this, 10 x to the 4th times 2x plus 1 to the 4th, plus 4x cubed times 2x plus 1 to the 5th. Here's one to practice on your own. You're finding the derivative of g of t, which is t minus 2 over 2x plus 1, all to the 9th power. Pause now. In this case, the inner function would be right here inside of the parentheses. Therefore, I'll make u t minus 2 over t plus 1. That makes this u to the 9th, g, because that's the function. And then g prime would be taking the derivative of the outer function, 9u to the 8th, times u prime, the derivative of the inner function. Then to take the derivative of u, recognizing that this is quotient rule, f would be t minus 2, g would be 2t plus 1, f prime would be 1, g prime would be 2. Therefore, u prime will be f prime times g, 2t plus 1, minus f times g prime, and I just put the 2 in front, all over 2t plus 1 squared. And then simplifying the numerator, 2t plus 1, distributing the negative 2, gives negative 2t plus 4, all over 2t plus 1 squared. And then the 2t's will cancel out. 4 plus 1 is 5. Numerator is 5. Denominator is 2t plus 1 squared. That's u prime. Now coming back over here, substituting back in, g prime will be 9 times t minus 2 over 2t plus 1, all to the 8th power, times 5 over 2t plus 1 squared. And then watch what I'm going to do next. I see that I have 2t plus 1 here, and I have it here. So I'm going to break out this exponent. I'm going to separate it and apply it separately to the numerator and denominator. This will become 9, and then t minus 2 to the 8th over 2t plus 1 to the 8th. I'll rewrite this, 5 over 2t plus 1 squared. And then combining factors, 9 times 5 is 45. I'm going to write that in front. Then I have t minus 2 to the 8th power. And now these are like bases, and I'll use exponent laws to just combine them. 8 plus 2 would be 10. So the denominator will be 2t plus 1 to the 10th power.